Excited to be here at the first Pi Colorado conference. I'm William Horton, and this is Cuda in your Python. Today, we're going to learn about how you can harness the processing power of the GPU from within your Python programs. But to start out, I have some bad news. Moore's law is dead. This is unfortunate. Moore's law basically was the idea that the number of transistors that you could fit on an integrated circuit would double every 2 years. It was originally 1 year. He reformulated it, but basically, roughly every 2 years, the number of transistors you could fit on the chip would keep going up. And he started with this data, and the left side is a log linear scale. So basically, the line means that it's doubling every year, and that's continued to hold across many decades. And in fact, Moore's law has been the foundation for being able to build some of the software that we're capable of building now because of these improvements in hardware. But recently, Moore's law has been running up into some difficulties, and those difficulties are physics. This is a representation of the highest level of physics that I attained. So I will not give you an in-depth explanation of these exact physical limitations. But basically, as things start getting smaller and smaller, you run into some fundamental problems with shrinking it, as well as some problems with power dissipation. So they start getting really, really hot. And if you want to know more, and maybe you know more physics than AP Physics C, you can look up Dennard scaling, and there's some interesting stuff there. But we're starting to run into some of these fundamental physical problems with continuing hardware progress. And people have been writing about this, a lot of articles, the end of Moore's law, death of Moore's law, all this. You might still question, like, this has been true for many decades, so should we really believe that it's going to end? Here's someone who I think is an authority on this. He said, I guess I see Moore's law dying in the next decade or so. And this is someone I really trust on this matter, because this is Gordon Moore. He said it in 2015. So I think we can at least imagine that things are going to slow down over the next couple years, and we might want to start looking for an alternative to just computing on the CPU. And that leads us to the question of why GPUs? Why am I giving this talk today? I think there's a tremendous amount of potential in the GPU and trying to alleviate some of these problems we're facing with the death of Moore's law. So a little bit of a history of the GPU. It's a graphics processing unit originally developed for gaming purposes. It was designed to be really good at matrix operations and parallel processing, because you can imagine to render a scene or to do shading, you're basically working on a 3D matrix of pixels, and then you might want to do operations on that. And that's basically what the GPU was set up to do really well. To understand a little bit more, we can compare the specs of some hardware. So this is a kind of high-end consumer GPU from Nvidia versus an Intel CPU. So you can look at the specs here, and you can see that the Intel CPU has 8 cores. The GPU has 68 of what are called streaming multiprocessors, and those roughly match up with core count on a CPU, but it also has over 4,000 of what are called Cuda cores, and those are kind of arithmetic units that can perform these operations. So you can see there's at least sometimes more processing units on the GPU. On the other hand, you can see that the base clock and boost clock of the CPU are much higher, almost 3 times higher. And so then you can start to understand kind of the trade-off in these two processing paradigms, where the GPU, you can do more things, but not as fast. And the CPU, maybe you can do not as many things, but your base clock is higher rate. And that gets down to a fundamental difference in how these are architected. So basically, this is a layout of the different chips, and the green represents arithmetic units. And this gets to the fundamental difference, and why GPUs can do this data processing faster is that the GPU is devoting a lot more transistors to arithmetic units, but the trade-off is it devotes a lot less, as you can see, to control flow and to cache. And those are things that are really important to making the CPU a general purpose processor. So this is kind of the trade-off, is the GPU can do a lot more of these adds and multiplies, but maybe your control flow can't be as complex, and your cache is going to be smaller. So this is kind of what it looks like CPU versus GPU, and what the GPU can do well on a hardware level. And in recent years, we've seen the rise of what's called GPGPUs, the idea you can do general purpose processing on the GPU. And it's just a shift in mindset of saying, well, maybe it's good at these workflows for video games, but maybe it can also do these workflows for data processing and machine learning. And so a lot of the hardware manufacturers came up with their own paradigms for programming their devices. So I'm going to talk about Cuda and Nvidia today because that's kind of the dominant one in the space now. But AMD has their own, and I should mention there's also open specifications. So this is kind of starting to grow as a programming paradigm. And so basically the fundamental questions I want to answer in this talk are, one, why GPUs? We just went through that. What is Cuda? Why would you want to have it in your Python? And then what's next? If you learn how to use this in your programs, what can you do with it? But before we get too far into that, I'll talk a little bit about myself, how I got here. So my work, I work on data pipelines and machine learning at Compass, which is a real estate technology platform. We're basically building tools to help agents do their work better. And we use a bunch of open source Python tools. I've listed a couple. I really like Airflow. Obviously, we use a lot of Jupyter notebooks for some of the machine learning stuff. And one recent project we launched, for example, is recommendations on our homepage. So if we have some of your listings that you've already viewed, we can serve you some of the similar ones from our inventory and say you might also be interested in this. And I will say, we haven't actually started using GPUs yet, but as we start to incorporate features like image and text, that's where people have started using GPU processing. And so what really got me interested in this stuff was some of my hobbies. I got really into deep learning through the Fast AI course, did a couple Kaggle competitions, mostly using PyTorch. And you can see this is actually my home server. I've got 2 GPUs at home. And I'll tell you, I built this after one weekend when I was in a competition and I was running a GPU on AWS and I forgot to turn it off. And people have experienced this before, right? And so on Monday, I woke up and I'm like, oh my God, what is my AWS bill? So at that point, I was like, okay, maybe it's better to build versus rent. And that led me to come up with this idea I call Horton's law. You see, I've repurposed a diagram from before, and this is basically a doubling of your AWS bill with the increase in your interest in deep learning. So just be careful out there if you're doing this kind of stuff. So in terms of the use of GPUs right now, the present, which you might have heard about some of these tools, is GPUs for deep learning. So there's a lot of frameworks, PyTorch, TensorFlow, a couple others. And that's part of what got me interested in giving this talk, is I made a PR to PyTorch last year that was basically moving some of the functionality of padding tensors from a Python implementation into the C++ side. And seeing the internals of that library got me thinking, well, how did they fit this all together? They've got a Python API, C++, and Cuda going on. But I think Cuda and GPU processing is also leading to a lot more than just deep learning. There's GPU databases, which people have been, I think, trying to build for a while. And this is just one recent example of Uber built an analytics database powered by GPUs. And even the thought of GPUs for the whole data pipeline. So Rapids is an effort, an open source effort from Nvidia to basically say, we won't just do modeling on the GPU, but also maybe data pre-processing and afterward data visualization and understanding your results. And maybe we can put this all on the GPU and just accelerate your whole workflow. So that's kind of what might be the future if we can learn how to use these tools in more of our programs. So to get to the question that you probably all wanted to know when I started this talk is, how can you start programming the GPU? And so I came up with a little bit of an example. This is a NumPy example, basically just adding 2 really big vectors. And so I'm going to show you the example. This would obviously run on the CPU and NumPy, and so I'll show you the example with GPU. That's the example with GPU. I'll show that to you again. OK, this is CPU. GPU, I highlighted the differences there, just a couple characters. And I benchmarked this example. I got about a 30 times speed up. So just that change is going to get you 30 times speed up. And that's it, basically. You can go home and program your GPUs. Thank you, thank you. Unfortunately, it's not quite so simple, so I'm going to talk about a couple different approaches to how you can get CUDA in your Python program. So what I just showed is a drop-in replacement. CuPy is a great library, basically a drop-in for NumPy. They try to emulate the exact same API that you already are familiar with. It supports indexing, broadcasting, the kind of things you might already like about using NumPy. Just to highlight a couple of API differences, because I made that example look a little bit too easy. In terms of data types, unfortunately, the GPU is not good with handling strings and objects right now, so it's limited to the NumPy data types that are numerical. Array creation, basically, you can do a NumPy array around a Python list. And CuPy, unfortunately, doesn't support that. So if you do that in your programs, you might need to tweak it a little bit and make a couple changes. And the last thing is, just because the GPU wants to always be operating on vectors and not scalars, if you have methods like sum that in NumPy are going to return you a number, in CuPy it's going to return you a zero-order vector with that in it. So those are just a few things if you want to actually start doing this in your NumPy code. And there's a couple other examples of CUDA drop-ins, so there's cuDF now, which is supposed to be emulating the Pandas API. There's cuML, which is a CUDA-powered scikit-learn. And I think these are pretty cool because it makes it easy if you're already familiar with these APIs and these Python tools to try to start using this in your workflows. Moving beyond drop-ins, you'd have to start writing what are called CUDA kernels. And so we'll talk a little bit about the CUDA API. So if you want to write custom CUDA code yourself, how can we do that? And the heart of that is threads, blocks, and grids. These are the main structures of kind of the CUDA programming paradigm. So to start with threads, basically threads are what are executing your CUDA code. And the important thing is these have a thread index in up to 3 dimensions. And basically, the thread index lets you say what part of the data should this thread work on. And why does the index have 3 dimensions? It has to do with the kinds of workloads that GPU programming is going to be good for. And so that's basically data parallel workloads. And the idea is that you have many of these threads, and they're all going to work on a different piece of the data and basically do the same thing. So if you're adding 2 really long vectors, you're going to have many threads, and they might just add one slice of that vector to another slice of the other vector. But they're basically doing the same kind of logic, just on different pieces of the data. And so this is like one example. Let's say you had 4 threads, and you have 9 elements in your array. You might say, OK, the first thread is going to do work on some of these elements. The second thread is going to do work on other elements. And the nice thing about this 1D example is you can come up with a rule for which piece of the array the thread is supposed to touch. So you can see, in terms of your thread to your index, it's basically the thread index plus the number of threads times I. And so you can come up with some kind of logic for assigning work to your threads. And in the 1D case, it's lines up because you have your thread index in 1 dimension, your data index in 1 dimension. In the 2D case, it gets a little bit tricky, and what thread is supposed to do work on which part of this array? You have to use modulos. This can get a little bit weird. The 3D example, I can't even really hold in my head. And so the nice thing about CUDA is basically they give you indexes that you can use in the same dimension as your data. And that just allows you to more easily do data parallel processing, because you can basically say your threads are basically a 2-dimensional structure, and your data is also a 2-dimensional structure, and that just makes it a lot easier to line up what each thread is supposed to be processing. So this is kind of the bottom part of the diagram I showed before. Your threads are grouped in this block, and in this case, they have 2 indexes, so they're indexed in 2 dimensions. In terms of blocks and grids, blocks organize your groups of threads, and they provide 2 main important functionalities. One is shared memory between threads in a block. The other one is synchronization mechanisms. If they're sharing the memory, they also need a way to do some basic synchronization. The block also can be indexed in up to 3 dimensions. And then the grid is basically just a group of blocks. So this is what it ends up looking like. You've got your grid, which is made up of blocks, and then each of those blocks is made up of threads. And that's kind of the main piece of the CUDA paradigm. And so as an example of some CUDA code, this is one piece that basically adds two-dimensional arrays. And so to understand this a little bit, the other important piece of the kind of CUDA programming is host and device. So to execute CUDA code, you need both a CPU and a GPU. So the CPU is referred to as host, GPU is referred to as device, and you transfer data between them as you need to do computation. And the _ global is used to mark the kernel, which is the piece of the code that executes on the GPU. And the other kind of special syntax is these angle brackets, which you use to specify the grid size. So basically, how many threads you want to end up with is a function of the size of your grid and the size of your blocks. So going back to this code, this is just an example. You can see you're calling this matrix add kernel below. And so the bottom part will run on your CPU. Once it calls this kernel, it'll start executing the code above. And you can also see that it's using these indexing things that I was talking about, block index and thread index. So one way that you can start putting this to use is Numba plus Cuda JIT, just-in-time compilation. So if you're not familiar with Numba, it's basically a just-in-time compiler. It's largely used for CPU to try to accelerate Python. For some things that you might use C++ for, people start to drop in Numba to accelerate their Python code. But it can also be used for GPU, which is pretty cool. And it lets you write functions like this. So you can see this is a Python function. You decorate it with this cuda.jit decorator. And then inside, you also are writing Python code. But basically, behind the scenes, when your program gets to this function, it's going to just-in-time compile and cache the basically CUDA machine code that you need to execute this, and then it will call that with your data. So this is pretty cool, because it allows you to still write Python, but behind the scenes, this is getting turned into the machine code that you need. There's some limitations because it's compiling this function. So exception handling, basically you can't use context managers, generators. Those are just a little bit too complicated for the compiler to be able to understand. And there's also certain features of NumPy you can't use within it. But it's still, I think, a great way to be able to still write Python and compile it behind the scenes. And there's a lot of cool features. So one of them is basically being able to access these CUDA features, but within your Python code. So the numba.cuda module exposes things like the thread index, thread synchronization, as well as there's certain CUDA atomic operations. And so they've also implemented those. So you can do numba.cuda.atomic.add. And behind the scenes, that's going to turn into this kind of CUDA basic operation. They also have a Cuda Simulator. So this can be really cool for testing. Basically, if you're writing this code and you don't have a GPU for testing, it will basically simulate that. And it's able to do that because it understands this and can compile it into kind of their CUDA runtime on the Python interpreter for testing purposes. It also has interoperability. So this is inspired by kind of the NumPy interoperability mechanism. But a lot of frameworks are starting to implement this. So you can basically do a zero copy changing your tensors between like CuPy, PyTorch. TensorFlow is working on it. So basically, without having to copy things back and forth, you can maybe work in different frameworks depending on what you need to do. So that's also pretty neat. The next thing is PyCuda. So PyCuda is kind of a scientific library, or at least its main applications were some of these scientific projects. It's one of the first libraries I found that has a paper written about it. So if you want to learn more about it, you can check out that paper, and it's pretty cool. But basically what PyCuda does is you write strings of CUDA in your Python code, and then it's going to compile that and allow you to execute it. So you can see here, the code in the string is an example of a CUDA kernel, but then it's letting you compile that within your Python program and then run it as a function that you can call. And some of the benefits that PyCuda gives you, automatic memory management. It has some nice helpers around data transfer, error checking, and metaprogramming. So to talk about those a little bit more, I think this is one of the big benefits is basically memory management in CUDA can be a little bit tricky, and PyCuda just ties that to the lifetime of Python objects. So once the object goes out of scope, it's going to be cleaned up. It also has some nice helpers for data transfer. And basically, like I said before, you have your host CPU, you have your device GPU. You're sending data back and forth. But if you're using PyCuda, they have these nice classes that you can basically say, this data is only going in, or it's coming out or in, out, and different combinations of that. And so it basically saves you a bunch of these steps you might have to do. So creating a CPU array, allocating on the GPU, sending it back and forth. This provides you a lot of helpers that might save you from that manual work. This one is a little bit weird. So this is from the Cuda documentation. It says, if an asynchronous error occurs, it will be reported by some subsequent unrelated runtime function call. And this can be a bit strange, I will admit. But the Cuda operations are async, and so it can't return a synchronous error. So they decided that it's just going to show up later in your program. So PyCuda is going to handle this for you in a nicer way and return those as Python exceptions. Metaprogramming is another strength of PyCuda. So basically, I talked a little bit about, you can do like the size of your grid, the size of your block, and those are kind of parameters that you need to tune to get optimal performance. And so PyCuda actually says, well, you don't have to try just kind of tweaking those. You can just try a bunch of them and figure out what's fastest. And basically how they do that is you can use a templating library. So this example uses Jinja, and basically say, I want to template in some of these parameters, and then I can just run it with a bunch of these and time it and get the performance that way. And so that kind of saves you from having to like run the Cuda kernel, then edit the source, and so this can be a really big win as well. And also, for the interest of comparison, I should say CuPy also has this kind of functionality. It's called raw kernel, and it's the similar kind of thing where you can write a raw string as your Cuda code, and it will compile it in your program. So the last thing that you might want to use is Cuda as a C or C++ extension. So this would give you kind of maximum control over your program. And someone who heard this talk basically asked me, well, at this point, why not just use C++? And I said, well, I'm giving it at a Python conference, so I have to talk about Python. But the real answer is there's a lot of libraries that are already doing this. PyTorch, TensorFlow, even NumPy. Basically what they're doing is putting a Python API on the performance of C or C++ or Cuda. And I think that's one of the strengths of our language is that when you need that performance, you can drop into the lower level, but still expose this nice user-friendly API. So there's documentation on this, extending Python with C or C++. They say it's quite easy to add new built-in modules to Python if you know how to program in C. And I'm like, Going through this, I will say it's maybe not quite as easy as the documentation will make you think, but I'm going to outline kind of the main challenges if you want to do this yourself. Basically, the two things you have to do is write or generate your C++ code, and then configure your setup.py to be able to compile Cuda and C++ and kind of get it all together. And there's a really good example of doing this end-to-end, and I'm just going to pick out a couple pieces of code from this, but this is going to be in my slides later if you're interested in seeing how it all gets put together. So in terms of how to write your C++ code, this is a really crowded ecosystem. When I started looking into it, there's so many options, but some of the main ones are Cython, Swig, you might have heard of that. There's boost.python. And in terms of what to choose, I think Cython is great. Compared to some of the other options feel like they're written for C++ developers who wanted to have some Python. Cython feels like it was written for Python developers who want to add some C++, which is kind of the scenario we're in. It's pretty actively maintained, used in a couple of open source projects. If you want more comparisons, there's this blog post that's kind of up to date in terms of what the ecosystem looks like right now. But Cython is cool. And the code looks like this. So if you kind of look at it, it looks mostly like Python. There's these weird C defs, which let you specify some like C types and things. But for the most part, it feels like Python with additional syntax. So I talked, those would be tools on how to connect your C++ code into Python. But another question is, well, how do you connect your Cuda code? Nvidia provides you with this compiler called Nvcc, and it basically takes your Cuda source code, it compiles it to GPU assembly, It also replaces some of the special syntax so that it is actually valid C++. And then you can also use, optionally, the C++ compiler to compile the host code. So the problem becomes then like, OK, I have host code that's C++, I have the Cuda kernel, I have my Python program. So you want to get this all together, and that requires configuring your setup.py and setting up an extension. So this is the documentation on making an extension. You use distutils. And at least here they admit, OK, it gets a bit more complicated at this point. So basically, an example of a setup.py that you can use is to say, OK, I have this extension. You specify the sources. And so .pyx is the Python extension. And then you're basically providing arguments that's going to tell it, OK, compile my Cuda with Nvcc, compile my C++ with GCC, link in these kind of system libraries that you need. But like I said, this can be complicated. And you might even be wondering, why do you want to do this? So some of the advantages, just having fewer dependencies. So you don't have to be worrying about versioning of libraries you depend on. So like if you're using CuPy, I mean, you have to figure out how to install that. And it might also make your library easier to ship around if you don't have dependencies on these other things. The other thing is manual memory management. So this is kind of a blessing and a curse. You see you have to call like mallocs, memcopies, freeze. But there are some benefits. This is going to give you like the most low-level control over your memory. And there's some memory features of Cuda. There's basically mapped memory and different ways of locking the memory between CPU and GPU. Some of these you can access with higher-level libraries. But to get the most control, you're going to want to drop into like custom Cuda code. And the last one is a compiler. And I know that's kind of controversial, but I will say when you're working on this and maybe you're unfamiliar with Cuda, having actual error messages and telling you where you messed up, that can be kind of a nice benefit. So finally, I've given you a couple of these different methods of using Cuda in your programs. So you might wonder, how can you get started? The first question is accessing a GPU. And the good news here is that a lot of resources are available for free. So Google Colab is kind of a notebook interface that you can run for free on a GPU on Google's servers. Kaggle kernels also is available for free. And then here's some pricing on cloud GPU instances. So about $1 an hour. Google Cloud, you have to attach a VM. So it's, I think, comparable pricing. So once you get access, I wanted to point out a couple of good resources. So this is, Udacity had a parallel programming Cuda course. And even though it's not like active, the resources are still online. You just have to watch out, because some of it hasn't been updated. And so installing the right dependencies, I had a lot of trouble installing OpenCV. That was a whole debacle. But it is a really good course and really good material. And then there's also a Rapids tutorial that happened at SciPy this year, if you're interested in kind of Cuda for the whole data science workflow. And finally, where you can go next with this. The first thing I would say is figure out, can you apply Cuda to your workflow? If you're already using NumPy, like I said, I think it's relatively straightforward to maybe drop in CuPy and see how that works for you. Next, I think you can start learning about different parallel programming algorithms and what having Cuda available might unlock for you. And then the last thing is there is a lot of interest in other kinds of hardware devices. So they say like XPU architectures. So there's now the TPU from Google, a lot of other companies working on their own hardware. Also like FPGAs are increasingly popular. And there's some Python libraries for working with that. So if you're more interested in the hardware side, there's also a lot of stuff going on. And so the last thing I'll say is if you get into this stuff, remember Horton's law. Turn off your cloud instances and go program the GPU. Thank you.